How does probability amplitude explain quantum mechanics? Imagine trying to predict the outcome of flipping a coin or rolling a die. Now picture doing that for tiny particles like electrons or photons, which behave very differently from everyday objects. That's where probability amplitudes come into play. They are the key to understanding how particles act at the smallest scales. In quantum mechanics, the way we describe a particle's behavior isn't just about simple chances. Instead, we use complex numbers called probability amplitudes. These numbers tell us about the likelihood of a particle being in a certain state or position. But unlike regular probabilities, which are just numbers between 0 and 1, probability amplitudes are more like mathematical waves. Their squared magnitude gives us the actual probability of finding the particle in a specific place or state. This approach helps explain phenomena that classical physics can't, like particles behaving as waves and creating interference patterns. At the heart of quantum mechanics is something called the wavefunction. Think of it as a mathematical map that contains all the information about a quantum system. The wavefunction assigns a probability amplitude to every possible state the system can be in. When scientists want to know the chance of measuring a particle in a particular spot, they take the absolute square of the probability amplitude associated with that spot. This process is called Born's rule, and it connects the math to real-world experiments. It's how physicists predict what they will observe when they measure particles. One of the most fascinating aspects of probability amplitudes is how they can interfere with each other. When a particle can reach a certain outcome through multiple paths, each path has its own probability amplitude. To find the total likelihood, you add up all these amplitudes, not the probabilities. Because these are complex numbers, they can add together in ways that either strengthen or cancel each other out. This is what creates interference patterns, like the ones seen in the famous double slit experiment. In this experiment, electrons or light waves pass through two slits and produce a pattern of bright and dark fringes on a screen, showing their wave-like nature. When quantum processes happen in sequence, the probability amplitudes multiply. For example, if a particle transitions from one state to another through an intermediate state, the total amplitude is the product of the amplitudes for each step. This multiplication will help scientists understand how quantum systems evolve over time. It's a fundamental part of how quantum mechanics predicts the behavior of matter and energy at microscopic levels. The development of probability amplitudes was a major milestone in the early 20th century. Scientists like Erwin Schrödinger and Paul Dirac created different ways to describe quantum systems using these complex numbers. Schrödinger's wave mechanics and Dirac's matrix mechanics both relied on probability amplitudes to accurately predict experimental results. This shift from classical physics to a probabilistic framework allowed scientists to explain phenomena like atomic spectra and particle behavior with much greater precision. Today, probability amplitudes are essential for modern quantum technologies. Quantum computers, for example, use superpositions of states and interference of probability amplitudes to perform many calculations at once. This could lead to huge advances in processing power for specific tasks like cryptography and complex simulations. In summary, probability amplitude explains quantum mechanics by providing a mathematical way to describe the likelihood of different outcomes. Its squared magnitude gives us the probabilities we observe in experiments. This concept helps us understand superposition, interference, and the unpredictable nature of particles at the smallest scales. It is a cornerstone of how scientists have uncovered the principles of matter and energy in the quantum realm.